Hey there. A few weeks ago, I got a question in the comments regarding log normal distributions of stock prices and how to use that to calculate probabilities. The question specifically asked for Excel. So we will do that, but I think what we'll do first is look at the Monte Carlo code we did from maybe a year ago at this point and show that the results of those simulations give a price distribution that is distributed log normally. And we'll do some calculations within Python in a Jupyter notebook, and then go to the Excel spreadsheet and do the same there. So this should be a relatively simple video, relatively quick, hopefully 20 to 25 minutes. So yeah, rather than just me sitting here yapping, let's get into a notebook and get into it. Okay, so like I said, we're going to play around a bit with a notebook. This is the notation we're going to use. S0 is our initial stock price. S is the current stock price at a time t. Sigma is going to be the implied volatility, and I'm going to, the reason I'm writing this out explicitly is because when you read documentation on these distribution functions, they often use sigma for the standard deviation. And in this case, we're going to use sigma for the implied volatility. R is going to be the risk-free rate, and T the time. So when I need to use either the mean or standard deviation, I'll probably just write out the words mean or STD to avoid ambiguity with things like the sigma here. So what I want to do is play around a bit with the Monte Carlo code we wrote a few months ago that kind of simulates a bunch of stocks randomly, so you can kind of generate statistics, probability of a touch, and in our case I believe we did a probability of making 50% on an option trade. The assumption there is that over very short times returns are normally distributed, and so what I want to do is we're going to use that assumption, generate a lot of stock returns, and then we're going to show that the actual stock prices at the end of all these simulations follow a log normal distribution. So this is what our log normal distribution looks like. So basically, let's just kind of zoom in so we can see it a little bit. It looks very much like a normal distribution, except you're dealing with the logs of the stock prices instead of just the stock prices. So let's shrink this back down. I'm not going to go over the Monte Carlo code. I just copied it and pasted it in. Again, we're using this notation S0. We're going to start our stock price at $100. We're assuming a risk-free rate of 1% annualized, and I just kind of straight lined it. I divided it by 252 trading days. I didn't bother working out any sort of compounding effects, but whatever. It's just a number. Our time step is going to be a day, and we're taking the implied volatility to be 75%. Just I chose this number because it kind of shows off the log normal type of behavior. I'm going to start off with like 5 simulations just to kind of show this 30 days, and then I'll put a link to the implied, not the implied volatility, the Monte Carlo video, so you can just kind of go over this code if you want. And then I'm just going to plot the results. So let's go back up here, run our imports, and then run this. And let me turn off that transparencies here. So alpha, we'll get rid of this alpha part here. Oops. Run. So you can see these are our 5 stock runs. So what we're going to do to generate our statistics is just grab the stock price for each of these runs at the last day, so at the 30th day. But we don't want 5 stock runs. We're going to want a lot more. I think I'm going to use 100,000, and that's going to cause all sorts of problems with the plotting, trying to plot 100,000 curves. So I'm just going to comment this out. Let's go back up here and set this to not 5, 100,000. Run. Cool. So we want to grab the last column of our X vector, I believe, which has all the stock prices. So X.shape is, each row is one simulation run, and each column represents a day. So we have 30 days plus the 0th starting day, so 31 columns. So we want all rows of the last column for our prices. So let's come over here. We'll delete the shape, and we'll just say prices is equal to X. All columns and the last, all rows, last column. Now let's just generate a histogram. So plt.hist. Let's see, x. How many bins do we want? Let's just start off with 100 bins. And let's just set the edge color so we could kind of see each individual bin. The edge color is equal to black. And let's put this actually returns some value. So n is the number of points within each bin. Let's have bins be the number, the array that defines the bins, and patches is basically a pointer to the patches is a pointer to the rectangles that make up the histogram. And this looks a bit dodgy. Something is off here, so let's see if I can figure out what it is. Oh, I passed an X instead of the prices. That'll do it. Prices. So there is our histogram. So actually I wanted 100 bins, not 1,000. There we go. That looks a little cleaner. So obviously this is not like a typical normal distribution bell curve. You kind of have this fat tail going off to as the stock price rises, and is bounded at the lower end by 0. It cannot go below 0. So let us make this into a probability distribution by coming up here. So it's not a probability distribution because the area under this curve is not equal to 1. Instead of having to figure that out manually, we could just come out up here and say density is equal to true. That'll make it a probability density, and I'm going to add a bit of transparency to these patches just to kind of make the plot easier to see. So alpha is equal to 0.5. There we go. So how well does this distribution up here fit these data? So what I'm going to do is just basically write out a function that returns this and just overlay it on top of this graph. So I'm going to come up here and actually add in a new cell and enter this function in. So define, let's just call the function log normal. So there we go. Here we have this function that just kind of returns this up here, and let's come back down to the cell where we do the histogram, and let's plot out this function for values. Let's say x is equal to lowercase x is equal to np dot linspace. So we have linearly spaced points from, I don't know, let's go from, what do you say, 40 to 200? 40, 200, and I'll just do 100 points. F is equal to log normal. Our stock price, or our stock price range there, our X, our sigma, R in T, and S0, I have it defaulting to 100, but I'll just set it explicitly. S0 is equal to 100. Does it calculate? Nope. Okay, so I think the problem was we never defined T. We defined DT up here, but when we did these definitions, they were scaled down for the Monte Carlo problem, so we had to scale down the standard deviation, the sigma, implied volatility from an annual to a daily, and likewise for the interest rate. So down here, excuse me, I'm just going to kind of re-enter them here. So let's just see if that runs now. Okay, it does. And let's just plot out the results. So plt.plot x comma f, and we will make it a black line. Matches our results pretty damn good. So if we want probabilities, now that we have the density function, we can just integrate them between 2 points. In fact, instead of just picking specific points, let's make sure this is actually a probability distribution and do the integral over all space, or at least the range I took the data from, 40 to 200. So that basically captures everything. So the integral of this on that range should be what? Well, if it's a probability distribution, it should be close to 1. It should be exactly 1, but there's some rounding errors and such. So if you remember our last video, NumPy has a built-in trapezoid rule type integrator called np.trapz, and we just pass in our prices, which we called, actually it's backwards. I always do this in MATLAB, which enters things backwards. So it's the function and the variables x in this case. So let's just run that, and we see very close to 1. So let's just come up here and get rid of it because we don't need it. Now, one of the nice things about having these kind of standard, very common distribution functions is they're programmed into SciPy and things like, even Excel has them. So we don't need to actually write out this function. We could just use the canned routine in SciPy. And we don't even have to do the integrals because the software that comes with the SciPy also has the cumulative distribution function. So we could just use that to get the areas, the probabilities instead of having to do all the integration by hand. So I think what I'll do is I will calculate using numerical integration. What's the probability of having the stock price between 100 and 150, basically using our trapz function, and then I'll do the same thing using the canned cumulative distribution function. So to do that, let's come up here and we're going to change our range from instead of 40 to 200. Let's change this to 150, 150, and this to 100. So we want basically the integral, the area under this black line here. So let's just call that prob from trapz. That is equal to np.trapz, trapz f comma x. Oh, let's print it out. There we go. So about a 41% chance, 40.5% chance or so. So let's just do the same thing now with the cumulative distribution function. And it's as simple as getting the cumulative distribution function at this endpoint here at 150 and just subtracting the two values. So now, so here is the documentation for the SciPy log norm object. Let's make it a little bit bigger. The interface is a little bit clunky, I find. Let's see here. Here is our cumulative distribution function. So it takes a bunch of arguments: the location, the scale, and this parameter s. How these relate to the standard deviations and means of the corresponding normal distribution is kind of defined up here. So I'll leave that for you to read, and I'll just come down here and then, in the interest of time, just kind of just make use of this CDF member function and do the calculation. So let's go back to our notebook. So let's calculate it at this point here. So let's call that, I don't know, we'll call it P1 for point 1. That is equal to lognorm.cdf. Our point is the first element of the x vector, so it's going to be 100. The standard deviation of the corresponding normal distribution. Well, that's that is equal to the implied volatility multiplied or scaled by the square root of time. So let's just put it up here and call it STD for standard deviation is equal to sigma times np.sqrt of time. Come down here and put it in, STD. The location parameter is equal to 0. Do I have an extra parenthesis here? Yeah, I do. Something looked a little off. Glad I caught it now, otherwise I'd have like one of my infamous typos here. And then we need to pass in the mean of this distribution exponentiated. So what I'm going to do is come down here, and right under here I'm going to say mean is equal to that, and down here I will just say exp np.exp mean. Let's just see if this runs. Yeah, I guess I got to explicitly say that this is the scale parameter. So, looks good. Let's do the same thing for the next point. So what I'm going to do is copy and paste this, call this P2. Instead of x0, we want the density function, or the cumulative distribution function at this last point, where we're at 150. So hopefully, and I should probably have checked this out before actually doing it, the probability is just the difference of these two, P2 minus P1. So print P2 minus P1, and let's cross our fingers. And before crossing our fingers, or maybe we could type better if our fingers were not crossed, P1. Boom, out to how many decimal places? 6, 7 decimal places? Pretty good. So let's just quickly knock this off in Excel, since that's what the original question was about. Okay, so here we are in Excel. This column A is going to be our stock prices, and to do the probabilities, we only need the two numbers that we're going to use in our cumulative function. But I'm just going to go from 40 up to 200, and I'm going to make this column B, the density function, just so we can plot it out and make sure we're getting something that agrees with what we got in Python. And then later we'll go and calculate the probabilities. We'll do the same one, like between $100 and 150. So okay, what we haven't done yet is fill out this. Our initial stock price was 100. Our sigma was 0.75. Our risk-free rate was 0.01. And we were at 30 days, and it has to be annualized, and we're using trading days. So it's 30 divided by 252. And we are also going to need from our Python worksheet a field for the mean and the standard deviation. So you're going to remember that the standard deviation is equal to, what was it equal to? It was equal to the implied volatility, so sigma times the square root of time. And the mean was equal to the natural log of our initial stock price plus the risk-free rate minus, I believe it was minus, I'll double check after I type everything in, the risk-free rate sigma squared divided by 2, close parenthesis, and I believe it was times the time t. Okay, so I fixed my typos here. So here's our mean. It's 4.57 something, and our standard deviation of whatever this is here. So the function we want is lognorm.dist. So let's switch back to the spreadsheet, and not the spreadsheet, the web browser, and just kind of look over that documentation. So here's the documentation, lognorm.dist. It takes in x, which will be our stock price, and the reason I calculated those means and standard deviations because they are the next two arguments. And excuse me, the last argument is a Boolean, which tells the function whether to return the density function if it's false, or the cumulative function, which is true. So the first thing we're going to do is use this in the false mode. So we're going to get the density function, and then when we calculate the probabilities, we will use the true to make it a cumulative function. So let's go back to the spreadsheet now and just kind of enter this function in. So this should be equal to lognorm.dist a3, our mean, which is, what's our mean? Our mean is F7. Our standard deviation is this guy. And we want false. So that looks good. Let's just kind of drag this down. And let's just visualize this plotted out so that we could see what it looks like. So there we go, the density function, and it looks basically like what we had before. So I'm going to just slide this over here. And now let us do the probabilities. So let's do the probability calculation here, and we will use the same nomenclature, P1, P2, and we were going from 100 to 150. So P1 was at the stock price of 100, P2 at 150. So log norm dot dist 100. Our mean is this. Our standard deviation is this, and now we want true. Name log norm rather than long norm. It kind of makes a difference. Cool. So now we have for the next one log norm. Oh man. Log norm dot dist 150 F7 G7 true, and our probability is equal to P2 minus P1. Awesome. 40.4, essentially 40.5%, exactly what we got with our Python notebook. Cool. Not too difficult. As usual, I will clean up the notebook and the spreadsheet a little bit, upload them to GitHub. And again, if you have any questions, feel free to leave them in the comments below. And until next time, I will see you.